Hi, my name is Stefan Kaemmer from Weaker Instruments. This is going to be a short introduction into our new ScanAsyst feature. We'll start with a short PowerPoint, just a couple of slides, and then go into a video showing you the setup and the functionality of ScanAsyst. Let's get started. There are a number of perceptions you have to deal with when it comes to AFMs. Number one is AFMs are just too difficult to use, and it takes quite a long time to become really professional operating one with good results, even just for when it comes down to just basic imaging. Second, it can be quite difficult to get a proper interpretation of AFM images, simply because there's just not enough information to distinguish or identify different materials that are on your sample. And third, most AFMs are more or less equivalent. We did two things to change these perceptions. One is we came out with ScanAsyst. ScanAsyst is a new imaging mode that features an automated image optimization technique, and by doing so we make it a lot easier and faster to achieve expert quality results. You will actually notice that in the following video the only parameter I'm going to change is the scan range. So everything else is adjusted completely automated by the ScanAsyst algorithm. The second one is peak force QNM. That's a new package that generates quantitative maps of nanoscale material properties, while at the same time images the sample non-destructively and at very high resolution. Technology enabling ScanAsyst is something we refer to as peak force tapping. And it works basically by modulating the Z position at a small amplitude and a frequency well below any resonance of your system. While the probe scans across the sample, by resonating the Z position, we basically measure a series of very fast force distance curves, fast determined by the speed of the modulation, of course. The peak force of each of these force distance curves is then used as the feedback signal. That of course brings us to the data type that we can achieve. We of course get a height or height sensor signal, depending on if you have a system with a closed loop sensor on it. You get an error signal, the peak force error in this case, and every time you get modulating signals, of course you can measure also some kind of phase signal. It should be mentioned that the phase you measure in peak force tapping is not exactly the phase that you measure in tapping mode, even so it's questionable that it will ever be completely clear what the phase in tapping mode actually is, except being a high resolution qualitative signal. Automatic image optimization is of course the game changer. It points out that peak force tapping is a much more stable method for an image optimization perspective than conventional tapping mode, and it has to do with the fact that in peak force tapping we actually measure forces directly, whereas in tapping mode we monitor basically a gradient change by measuring a change in amplitude typically. The optimization algorithm continuously monitors the quality of tracking, the noise on a scan line and other parameters, and it uses these inputs to adjust the imaging parameters. And parameters that can be changed automatically are set point, the feedback gain, scan rate, and the limit. If you desire, you can disable the optimization entirely or individually, and then go ahead and change these parameters by hand. So if we want to summarize ScanAsyst here, the automated image optimization results in faster, more consistent results, completely independent of the user skill level. Because of the direct force control used, the ScanAsyst can work at ultra low forces, and those helps protect a delicate sample and all the tips from damage during the imaging process. And being a sub-resonant technique, cantilever tuning is completely eliminated, and that of course makes it much easier to scan, and is even applicable to imaging in fluids. There's basically no difference from a user perspective, imaging in air and or in fluids. To finish up the short slide presentation here, we are looking at an image of molecular brushes here. a 2 micrometer scan with the insert at about 750 nanometers, clearly showing the molecular change in that image. That was done at extremely low forces, and again, fully automated. The only thing the user had to do is put in a tip, a line, and hit engage, and then select the scan size. From that point on, everything was handled automatically by the system.